Hi there, welcome to Mr. Morgan's Math Help. This is Algebra 1, Unit 2, Lesson 4. It's called the Inbetweeners. And so today's lesson was really supposed to be about looking at the meaning of a fraction as an exponent, meaning we were taking a look at, the reason it's really called the Inbetweeners is we've been so far talking about like whole numbers, 1, 2, 3, and the question is what happens in between those intervals between 1 and 2? You're going to have a 1.5 and things like that. But we can also talk about values that happen between those spaces there. And sometimes we look at a fraction. A fraction can actually be an exponent. So in today's lesson, we went through several different kind of activities to kind of see how you would graph those things there. You started with some basic graphings of regular exponential things to kind of see how things would look. But then as you moved along, you started talking about, okay, what happens in the in-between the whole number values there? And looking, seeing what would happen to your output when your input became a fractional value. Okay, and that's really what today's lesson was, is practicing those things to take a look at how that would affect your inputs and outputs there. So, as a summary then, in this lesson we developed meaning for us using a fraction as an exponent. We began with a geometric sequence and found a way to fit data at the points halfway between whole number inputs in a way that would maintain the multiplicative behavior of the sequence. We continued to work with different fractional inputs and gave meaning to using a variety of fractions as exponents. So in the past, we knew that something like 2 to the third power was the same as 2 times 2 times 2. And what today's lesson really was talking about was, what if I have 2 to the 1/2 power? What does that mean? And really today's lesson, we learned that actually means the square root of 2. Okay, and we could justify that by saying if I knew that 2 to the 1/2 power, what is 2 to the 1/2 power? It means if I know that 2 times 2 to the half power times 2 to the half power becomes 2 to the 1/2 plus 1/2, which is 2 to the first power, then what I also could say is that's similar to saying the square root of 2 times the square root of 2 is equal to 2. 4 is equal to 2 as well, because those roots are going to cancel them out, okay? So what we're saying essentially is that 2 to the 1/2 power is the same as the square root of 2. Another way of saying what we're talking about today is that any base to the 1 over n power is equal to that base to the n root power. And we say n root power because sometimes it might be a third or cubed root, something like that, not just always a squared value. Okay, and that's kind of what today's lesson was about. Another thing we talked about today in the lesson was that if you had a to the m over n power, then that becomes the n root of a to the m power. Okay, and that'll come up today in some of our homework parts. Okay, so looking at fractions as an exponent, it's saying that that's okay. So let's start off with just the retrieval part here, which is kind of review things to help you get ready for today's lesson. So for these sequences here, find the next two terms and decide whether it's arithmetic or geometric, and then make the explicit equation. So we're going 4 to 12 and then 12 to 36. So clearly I'm doing more than adding here. If I had to guess, I'm saying I'm multiplying by 3. So the next two terms would be 36 times 3, which is 108, and 108 times 3, which is going to be 324. So those are going to be our next two terms there. Because we're multiplying, we're going to say it's geometric. And then so for our equation, what we would say is we can say that y equals, and we have where we start at, 4 times 3, because that's what we're doing, to the n minus 1 power. All right, so for b, we can see we're going 4 to 12. Could be either times 3 or it could be plus 8. So 12 to 20 is not times 3, it's definitely just a plus 8. Meaning our next terms are 20 plus 8 is 28, and 28 plus 8 is 36. So because it's adding 8, this is going to be arithmetic. And we're going to say our equation is y equals 8n, because that's what's happening. And then we're going to have to say, well, as a table, think back to your table. You have 1 when x is 1, or when the input's 1, y is at 4. And we know we're adding 8. So to find out what this value is, I need to figure out what would be at 0. So if I subtract 8, I'm going to be at negative 4. So we're going to say y equals 8n minus 4. Okay. So 160 to 40, we could say it's subtracting 120, but that's not what's happening there. 40 to 10 is going to be, looks like, multiplying by a fourth. That's what it looks like. So if we take 10 over 4 for the next one, that becomes 5 over 2. That's our first value. We multiply that by a fourth, then we end up with 5 over 8 as our second value. So those are our two values. We can tell that it's geometric because we're multiplying by a fourth. And so then for our equation, we would say y equals the first value times what we're doing, 1/4 to the n, or x minus 1. So we could say n minus 1, x minus 1, whichever one you want to use there. Probably in this case, since we're using y, we would say x, just to stay consistent. Probably should come back over here, make that an x as well, and make this an x as well. Once you switch to x and y, we should do that there. Okay. Before we were doing f of n and n. So once I switch to y, I should stick to x and y. And on the last one here, we see we're going up 20, or times 2, but we're definitely adding 20, it looks like. So my next terms are going to be 80 and 100. And this is going to be arithmetic because we're just adding. And so we're going to say y equals what we're doing, 20, adding 20x, plus, and I need to go back to kind of where we started at. If I think about at 1, we're at 20. At 2, we're at 40. So 0, I need to subtract 20, which means I'm going to be at 0 actually. So I don't need anything after it. I can leave it just like that for D. The other part, to kind of get you ready, reviewing things here. The bases are the same, so I keep the same base. I'm multiplying, so I want to add those. 2 plus 3, so I get 7 to the 5th power. Here, because I'm dividing, I'm going to do subtraction. Keep the same base, 5 minus 2, which becomes 13 to the 3rd power. Over here, we have something to the 0 power. Anything to the 0 power is simply going to be 1. And this one, 5 to the negative 7. When I see negative 7, it means it's got to move downstairs. So we're going to say 1 over 3 to the 7th power. All right. So now let's take a look at your homework. Hopefully you've already done that on your own, and you're just here to kind of check and make sure you're getting the hang of it. So let's take a look at tonight's homework problems. All right, we have sequences below exemplify a multiplicative or geometric pattern, or multiplying. Fill in the missing values, and then write an explicit equation. Okay, so we're multiplying by something to get up. We can tell from 2 to 64, we're definitely multiplying by a whole number. Okay, by a whole number because it's getting larger. So let's just start with some basics. Let's just try something like 2. If it's 2, I'm going to go 2, 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. So I'm right on track. Fill them out, 128 and 256. So for our equation, we would say that, in this case here, y equals, and what are we doing? We're starting with our first value, 2 times whatever we're doing to the x minus 1 power. You could also write it as f of n equals 2 times 2 to the n minus 1 power. Both of those are okay. All right. For our next one, we see we're at 360 to 45. We're definitely decreasing. So I'm going to be multiplying by some sort of rational number. It's going to be a fraction in this case here. So let's just start with something like a half and see what happens. So half of 360 is going to be 180. Half of 180 is 90. Half of 90 is actually 45. So I'm on target. Looks great. Half of 45 is 22.5. Half of that is 11.25. Half of that is 5.625. And half of that is 2.8125. Okay, lovely. As an equation, we would say f of n equals our first value, 360, times what we're doing, 1/2 n minus 1. All right, next one. -3, we're going to -384. It is increasing, right? In one sense, I know it's going down negative, but it's still multiplying by a whole number to get there. It's not becoming a like a smaller value, so to speak. Okay, so let's just try multiplying by a first. Let's try multiplying by 2 and see what happens. If I multiply by 2, I'm going to have negative. I'm going to have well, decide. Multiply by 2, I'm going to go with -6. Multiply that by 2, -12, -24, -48, -96, -192, and -384 actually works out fine. So I'm multiplying by 2. Because I'm multiplying by 2, we would say, we know it's geometric, so our equation is going to be f of n equals our very first term, minus 3, times what I'm doing, 2, to the n minus 1 power. Number 4, we see we're decreasing from 972 to 4, so I'm multiplying by some kind of fraction. I could think, maybe I'm multiplying by a half, maybe I'm multiplying by a third. Those are all options there that you want to explore. In this case here, when I was exploring it, I found out that it was best to do by a third. So if I multiply by 1/3, 1/3 of 972 is 324. 1/3 of that is 108. A third of that is 36. A third of that is 12. And a third of that is indeed 4. And a third of that, I could either say it's 4/3, or I could say it's 1.33. And then a third of that is going to be 4/9, or I could say 0.44, like so. So it depends on if you would fractions or decimals. As an equation, f of n equals our first term times what we're doing, multiplying by a third, to the n minus 1 power. All right, now let's play with some square roots, which is a little bit what the lesson was about today. So we're going to rewrite each of the square roots below by removing repeated factors from under the square root. Example, you take the square root of 8, and instead of calling it 8, you call it 4 times 2, and then you can know what the square root of 4 is, which is 2, and then you leave the square root of 2 as left by itself. So for something like 75, 75 is a combination of 25 times 3. Now as a square root, the square root of 25 is actually 5, because 5 times 5 is 25, and then what's left over is just the root 3. So we leave it like that. For number 6, I want to think about what multiplies together to get 6 and 3. In my case, I know that 9 times 7 is 63. The square root of 9 is 3, and there's not really a square root of 7, so we keep it just like that. So we would say 3 root 7. For 18, again, we're going to think 9 times 2. So we're going to square root of 9 times 2. Square root of 9 is 3, and we're left with a root 2. 98 is not one I'm super familiar with there. So if it's a big number like this, what I did first of all is I divided it in half. So I did 2 times 49. And once I did that, I realized, oh, I know the square root of 49 is actually 7. So it's 7, and what's left over is still the root 2. So just break it apart into smaller parts. Just tell us to see when you can find a repeated factor there. Okay? All right. All right, fill in the missing values of the table based on the growth that is described, then create the explicit equation. So we have the in-between values here today, right? We can see that from going from 0 to 1, from here to here, we're multiplying by 3. Okay, so that's what's happening right there. We're multiplying by 3. So I could fill in the other ones here. This is going to multiply by 3. And so 6 times 3 is 18. 18 times 3 is 54. And 54 times 3 is 162. But I also want to get the in-between values, right? I want to say what's happening in between there. Okay, so to do this here, what's helpful is I know that it's tripled at each whole interval, which is great. But at this point, the question is what's happening at the 1/2 interval? Well, let's think of it this way. Let's look at our equation. For our equation, we're going to say that f of n equals the first number, 2, times 3, because we're multiplying by 3, to the n In this case here, we're going to say the n power. And the reason it's the n power, again, is because 3 to the 0 is equal to 1, and that leaves you with 2. So that's perfect there. So now let's see what happens if we plug in the half right there. Well, I'm going to say that f of n, when n equals a half, let's see what happens. I'm going to say 2 times 3 to the 1/2 power. Well, what is that? We said before in our warm-up that 3 to the half power is the same as square root of 3. So when we put a half in there, we're going to say it's equal to 2 root 3. Okay? How about the next one? What is 2 times 3 to the 3 over 2? Well, I have 2 times the square root of 3 cubed. So 3, 3, 3, right? That's what I have there for this one. I'm going to draw a little line there. So 3 times 3 is 9, which means I can kind of factor that out, and because it's kind of doubled up, right? That I can pull a 3 outside and have 2 times 3 root 3, which becomes 6 to root 3, or 6 root 3. Now you can see, hopefully at this point, a little pattern, right? The next term is going to be, you take the previous term 2, and then we're multiplying it by a root 3, 6 root 3. And in fact, all these become just like that. That pattern continues all the way. All right, so it helps to plug that value in to take a look and see what's happening. We could try it real quick and take a look at 5 over 2. So that would be like doing 2 times 3 to the 5 over 2 power, which is 2 times the square root of 5 threes. 1, 2, 3, 4, 5. And by doing that, when I have a group like that, and I find a partner or a match, I can now pull them outside of the radical. So I can say 2 times one group of 3, another group of 3, with one square root of 3 left. 2 times 3 is 6, 6 times 3 is 18, and that becomes 18 root 3, which is what you can see right there, right? So just showing how that actually worked. Okay, that's a great little problem there, showing the in-between values. Let's take a look at number 10. Same idea. We see it's tripled each year. So once again, the same thing is going to be taking place, right? F of n is going to equal your first term times 3 to the n power, okay? Because it's tripling every time. So what happens to this 1/3? Well, let's plug it in and see. We have 2 times 3 to the 1/3 power. So you end up with 2 times the cubed root of 3. Okay? The cubed root of 3 because it's 1 over 3, not 1 over 2. Remember, 1 over 2 is just a square root. When it's 1 over 3, it's a cubed root. All right? So the value here is going to be 2 and the cubed root of 3. For the next one, we would say it's going to be 2 times 3, 2 over 3. So you end up with 2 times the cubed root of 3 times 3. And 3 times 3 is going to be, in this case here, 3 squared. But we're doing a cube root, so we can't take it out of there because it's going to be cubed. So 3 times 3 is still going to be 9. So we're going to leave it as 9. So we're going to have 2 and the cubed root of 9. And the next one's 6. And then we have 18, and so on and so forth, okay? So we're going to need to fill those values in to see what happens with the next one. So if I did 2 times 3 to the 4/3, then that's 2 cubed root of 4 threes. 1, 2, 3, 4. And because of the cube root, I can now take out one of those 3's. So I'm going to have 6, because that's 3 times 2. And then cube root of 3. So I have 6 cube root of 3, which means my next one, following the pattern, is going to be 6 cube root of 9. And that means this is going to be 18 cube root of 3, and then 18 cube root of 9. All right, and number 11. All right, we're growing by a factor of 4 each year, so it's times 4. So we know with our equation, we're going to have our first term, 2 times 3. Oh, sorry, not times 3, times 4. We just said it. Times 4 to the n power. All right, and so for the first one that's a half, it's going to be 2 times 4 to the 1/2 power, which is 2 times the square root of 4. The square root of 4 is actually 2, so we're going to say it's equal to 4. For the next value, it's 2 times 4 to the 3/2, so that's going to be 2 times the square root of 4 times 4 times 4, right? Okay, so 4 times 4 times 4, well, square root of 4 is 2. Square root of 4 is 2, and square root of 4 is 2. So now I have 2 times 2 is 4, times 2 is 8, times 2 is 16. Okay, and we know this next one here, because I'm multiplying by 4, is going to be a 32. Multiplying by 4, and we have 128. And multiplying by 4 for the next one, we have 2, 3, 12, 15, carry the 1, 4, I messed up here, sorry, 128 times 4, 2, 3, 8, 9, 10, 11, and then 512, sorry, 512. Then we have to fill in the other ones. And basically you can see what's happening is we're doubling each time. So this is going to be 64, and this would be 256. So you can do the math and figure that out for sure, but it's playing with those those fractional exponents there. All right, excellent. Going to the go section, our last section here. Rewrite the exponents using the rules you know. All right, bases are the same, so that stays the same. We're multiplying, so that means we're going to add the exponents. 2 plus 5 becomes 3 to the 7th power. Here we're dividing, so we're going to, and the bases are the same. So we're going to subtract 3 minus 2 becomes 5 to the 1st power. Rewrite that one as 1 over 2 to the 5th because it's negative, needs to move downstairs. Any number to the 0 power is simply equal to 1. Here, we're multiplying, and we could think of it however you want, really. There's a couple ways to approach this one. Let's do one at a time. Here we have 7 times 5 minus 2 times 7 times 3 minus 4. Well, this becomes 7 to the 3rd times 7 to the minus 1. So now we add those up, and 3 minus 1 is 2, so we're left with 7 squared. For this next one here, we can kind of group these all together. This becomes 3. We're all multiplying, we're adding, subtracting, because we're multiplying, dividing. So I have minus 2 plus a 5 minus a 7. So there's my minus 2, there's my 5, and that's my minus 7. So minus 2 and minus 7 is negative 9, plus 5 making negative 4. So we have 3 to the negative 4 power, or written properly, it's 1 over 3 to the 4th. All right, and that's really it for today's lesson. Hope that helps you out a little bit of the homework. I know some of those fractional ones take a little bit more work to kind of work out on paper. Just take your time, and you'll see some patterns that develop as well. And that's it for now. We'll see you next time.